Friends, in the fourth part of this series, we are going to see now the FTIR, that is Fourier Transform IR spectroscopy, its theory, instrumentation, and applications. So let us see what are the third generation FTIR spectrophotometers. They have certain distinct advantages over the earlier one. Their signal to noise ratio of the spectrum is significantly higher and productive than the previous generation infrared spectrophotometers. Their accuracy is also of wave number is also very high, and error is very small within the range of plus minus 0.01 centimeter inverse. The scan time is also very short, approximately 1 second. The resolution is extremely high, 0.1 to 0.005 centimeter inverse. The scan range is wide, that is 1000 to 10 centimeter inverse, and the interference from stray light is highly reduced. And due to all these advantages, FTIR spectrophotometers have replaced the traditional dispersive IR spectrophotometers. Why do we choose an FTIR spectrophotometer over a dispersive instrument? Because the spectral region is in the infrared, high spectral resolution is required, applications involves weak signals, so you have to be very sensitive to even stress them. The spectra needs to be acquired quickly with high sound and noise ratio, and high spectral accuracy is required. Due to all these reasons, these are the reasons for the preference to FTIR spectrophotometers. Now, FTIR spectrophotometers, let us go to the theory part in short. Any waveform can be shown in one of the following two ways, either in the frequency domain or in the time domain. Now, all dispersive IR instruments operate in the frequency domain only. There are, however, advantages to be gained from measurement in time domain followed by computer transformation into frequency domain. It could be possible to do so by allowing radiation to fall on a detector and recording its response over time. So time is used as a variable instead of frequency, and then from analog to digital the computer transform it for an easily understandable IR spectrum, which is again represented in the form of wave numbers. Basically, an FTIR, what is an FTIR spectrometer? It is a spectrometer that collects all wavelengths simultaneously. This is very important, and this feature is called as multiplex or Felget advantage. The dispersive won't. They have a narrow slit. They collect one by one the frequency, but this particular thing collects everything simultaneously. So what is the multiplex Felget advantage? In a dispersive spectrophotometer, wave numbers are observed sequentially one by one as the grating is scanned, while in an FTIR spectrophotometer, all the wave numbers of lights are observed at once. When spectra are collected under identical conditions, that is, spectra collected in the same measurement time at the same resolution with the same source, detector, optical throughput, and optical efficiency on dispersive and FTIR spectrophotometers, means identical conditions, the signal to noise ratio of FTIR spectrum will be much greater than that of the dispersive spectrum by a factor of nu m, where nu m is the number of resolution elements. This means that a 2 centimeter inverse resolution 800 to 8000 centimeter inverse spectrum measured in 30 minutes on a dispersive spectrophotometer, and with the same thing with an equal sound to noise ratio on an FTIR spectrophotometer will require only 1 second. So this is a fantastic speed it has. FTIR's Fourier Transform infrared spectrophotometer obtains an infrared spectrometer by first collecting an interferogram of a sample signal using an interferometer, then performs a algorithm or a calculation called as a Fourier transform on this interferogram to obtain the spectrum. So it first collects an interferogram. It's a type of time domain graph actually of the sample signal, and for this it uses an interferometer, and then it performs complex calculations on this using an algorithm called as a Fourier Transform and converts it into a spectrum. An interferometer is an instrument that uses the technique of superimposing interfering two or more waves to detect differences between them, and for this the FTIR spectrometer uses a typical interferometer called as Mitchellson interferometer. Now let us see the components of FTIR spectrophotometer. The common FTIR spectrophotometer consists of a source, that is interferometer, and sample compartment. So the source, the source, and then this is a collimator, then this is an interferometer, then this is a sample compartment, and a detector, and then there's an amplifier, and then it's analog to digital converter, AD converter, and finally it is a computer which gives you the graphical output in form of a spectrum. The source generates radiation which passes through the interferometer through a collimator, which is focusing that, and reaches to the detector via the sample. Then a signal is amplified and converted to a digital signal by the amplifier and analog to digital converter respectively, and eventually this is transferred to a computer in which a Fourier transform is carried out and it gives a graphical output. The Fourier transfer optical system diagram, let us see this little bit in a much animated fashion to understand the mechanism. So let us first go to the light source, and this is basically infrared energy is emitted from a glowing black body source and ends at the detector. So this is starting from the light source, it falls on the mirror, and from which it is now directed to the interferometer. This entire thing is an interferometer. These are the components of the interferometer, and beam enters the interferometer where the spectral encoding starts taking place, and first it falls on the beam splitter, which takes the incoming beam and divides into two optical beams. It is dividing it into one and two optical beams. Okay, so one enters the sample and another enters the beam enters the sample compartment where it is transmitted through and reflected off the surface of the sample. Okay, so there is nothing called reference here. This first goes to the movable mirror, and this goes to the fixed mirror, and then it again gets reflected back again to the beam splitter, and from the beam splitter it is again reflected by another set of mirror, and then it enters the sample compartment where it is transmitted or reflected through the surface of the sample. Okay, and it goes to the detector, which is DLA TGS, that is deuterated lanthanum alpha alanine doped triglycerin sulfate detector, and this is called as a Mitchellson Interferometer, where one mirror is fixed and another keeps on moving, and therefore this has got a fixed length of falling and reflection, but this keeps on varying, and so these two are collected and analyzed, and if these two are matching, then there is a gain, and if they are different, then there is a destructive interference and constructive interference we are going to see in the next. We're going to see the Mitchellson Interferometer MI in much more details, and is the core of the FTIR spectrometer. It splits one beam of light into two, so that the paths of the two beam are different. And this is a source, and this is a splitter, and this splits into two parts, and these are again reflected back, and then these are going to the detector. And that recombines the two beams and conducts them into the detector with the difference of, and it also reflects it back to the source. So 50% goes to the detector, 50% goes to the back. So the two beams and conducts them into the detector where the difference of intensity of these two beams are measured as a function of the difference of the paths. The Mitchellson Interferometer consists of two perpendicular mirrors and a beam splitter. So these are two perpendicular mirrors. One is of course a fixed or stationary mirror, and another is moving mirror. So like if this is the length, this is the length, and this is moving along this length, so this keeps on varying. Okay, this is same is again nicely explained, only this part only we are focusing on the MI. And this is an input, and this is a beam splitter, and it is splitting into two parts. One is a fixed mirror, one is a moving mirror, which keeps on moving like this. And this is again coming back, and this is again divided into two parts, goes back to the input and goes back to the output, that is the detector. The beam splitter transfers half of the light and reflects half of the light back to the source. Subsequently, the transmitted light and the reflected light strike the stationary mirror and the movable mirror respectively. When reflected back by the mirrors, the two beams of the light recombine with each other at the beam splitter. If the distances traveled by the two beams are the same, which means the distances between the two mirrors, if this and this, and the beam splitter are the same, the situation is defined as zero part difference. But imagine if the movable mirror moves away from the beam splitter, moves away. The light beam which strikes the movable mirror has to travel a longer distance than the light beam which strikes the stationary mirror. The distance which the movable mirror is away from the zero part difference, that is the additional distance which it has moved as a mirror displacement, is represented by delta. And it is obvious that the extra distance traveled by the light which strikes the movable mirror is 2 delta, because it goes and again comes. So it's the light goes and again comes, so 2 delta. This extra distance is defined as optical path difference, OPD. So you have got a zero part difference and you have got OPD, and is represented by delta, small delta. So let us see. So this extra distance is defined as optical path difference, OPD, and represented by delta. Therefore, delta is twice of this delta. It is well established that when OPD is the multiples of the wavelength, constructive interference occurs, because crests and overlaps with crests. Crest will overlap with crest, troughs will overlap with troughs. As a result, the maximum intensity signal is observed by the detector, and the situation can be observed by the following equation. Delta is equal to n wavelength. N can be 1, 2, 3. In contrast, when the OPD is half the wavelength or half the multiples of the wavelength, the destructive interference occurs because crests overlap with troughs. So there is a mismatch. Consequently, a minimum intensity signal is observed by the detector, and this situation can be described by the following equation. Delta is equal to n plus 1/2, you can say lambda. These two situations are two extreme situations. If the OPD is neither n-fold wavelength nor the n plus 1/2-fold wavelengths, the interference should be in between these constructive and destructive. So the intensity of the signal should be between maximum and minimum. Okay, and since the mirror moves back and forth, the intensity of the signal increases and decreases, which gives rise to a cosine wave. And the plot is defined as an interferogram. It is in the wave function and it is in the time domain. When detecting the radiation of a broadband source rather than a single wavelength source, a peak at zero path difference is found in the interferogram. At the other distance scanned, the signal decays quickly since the mirror moves back and forth. So the Fourier transform of interferogram to spectrum. So the process of converting the interferogram to a spectrum, understandable spectrum, means from time domain to frequency domain, is this mechanism is called as a Fourier transform. The interferogram is a function of time, and the values yielded as output of this function of time are said to be made up of into time domain. The time domain is Fourier transformed into a frequency domain, which is on deconvolution yielding a spectrum. So this figure below, this is a time domain, this is what you can say an interferogram, and this is a spectrum. So this is a time domain and this is a frequency domain, and the algorithm by which or the set of equations, integrations and other things performed is called as a Fourier transform function or mechanism. So Fourier transform, named after the French mathematician and physicist Jean-Baptiste Joseph Fourier, is a mathematical method to transform a function into a new function. It defines a relationship between a signal in time domain and its representation into a frequency domain. So this is a time domain, these are interferograms, and this is spectra. Being a transform, no information is created or lost in the process, so the original signal can be recovered from Fourier transform and vice versa. The Fourier transform of a signal is a continuous complex valued signal capable of representing real valued or complex valued continuous time signals. So, well, unlike the dispersive spectrophotometer, all frequencies from the source are measured at one time collectively, and because the interference between light reflecting from the stationary mirror and that from the moving mirror, the energy observed by the detector shows an unusual pattern over time, and this is called as interferogram. So this is signal versus time, and a typical interferogram. The maximum occurs when the moving mirror is at the same distance as the stationary mirror. We get a constructive interference. But if it moves away, then you get something different. So this light wave 1 and light wave 2, one is of moving and one is of what you can say fixed mirror, and they will add and you get a constructive. But if because what is happening is trough is matching trough, crest is matching crest, and therefore they are perfectly. But here what is happening is the trough is matching crest and crest is matching trough. So this is really the destructive, and so finally you get a smaller one. And destructive interference is with respect to the equal amplitudes. If the troughs and crests are of equal amplitudes, then you will get a flat line. So here you get somewhere flat lines and somewhere these are only the constructive interferences, these are the destructive ones. So is FTIR qualitative, quantitative or comparative? It is both, I can say. It is qualitative because each different material is unique combination of atoms and no two compounds produce exact same infrared spectrum. The size of the peaks in the spectrum is a direct indication of the amount of material present. Quantitative and comparative, since it is sensitive, accurate and has software algorithms, the quantitative methods can be developed and calibrated easily to perform various analysis. FTIR is comparative due to the background spectrum that is compared to that of the sample. Advantages, it's very speedy, very sensitive, it is mechanically simple, internally calibrated, and too sensitive that it would detect the smallest contaminant. Other advantages are improved frequency resolution, improved frequency reproducibility compared to the older dispersive instruments which must be recalibrated after each use. Higher energy throughput, computer-based, allowing storage of spectra and facilities for processing the spectra, and the sample is not subjected to thermal effects. So to summarize, Fourier transfer infrared spectroscopy is a technique used to obtain an infrared spectrum of absorption or emission of a solid, liquid or gas. An FTIR spectrometer simultaneously collects high spectral resolution data over a wide spectral range. In FTIR analysis, infrared light from the light source passes through a Mitchellson Interferometer along with the optical path. The light beam split into two by the beam splitter is reflected from the moving mirror and the fixed mirror before being recombined by the beam splitter. What is the difference between IR and FTIR? FTIR is a spectroscopic technique. Fourier Transform infrared spectroscopy is used to determine the functional group in any organic sample given dipole. With a given dipole, if a given dipole moment exists, as dipole moments that change as a function of time are capable of absorbing infrared. FTIR analysis is used to identify and characterize unknown materials like films, solids, powders or liquids, identify contamination or in a material, example particles, fibers, powders or liquids, identify additives after extraction from a polymer matrix. Pyroelectric detectors have fast response time, so they are used in most of the Fourier Transform IR instruments. Photoelectric detectors such as mercury, cadmium, telluride detector comprise of a film of semiconducting material deposited on glass surface sealed in an evacuated envelope. The transparency of the material from which the beam splitter is made is a crucial factor in determining the wave number range over which the instrument can operate. The commonly used material KBR allows transmission of IR on a wide range of 370 to 10,000 centimeter inwards, while other materials permit other operational ranges. KBR does not show any absorption in IR's spectrum region because it is totally transparent, and 100% transmission window it has in the range of wave number 400 to 4000, that is the mid-infrared region, with electronegativity of 2 based on the Pauling scale. An FTIR spectrometer device is precisely calibrated by using a polystyrene calibration film. It is always good to first calibrate because size of peaks are you should check whether polystyrene has a reference spectrum. So you should run a spectrum every time with this polystyrene film. Just put the film in the sample holder. It is made at that size only and of similar design. And you should get a spectrum which should match with the reference spectrum. That means things are okay. You are getting the same size of peaks corresponding to the amount of material. Applications of IR spectroscopy, infrared spectroscopy is applied to the qualitative and quantitative determination of molecular species of all types. Most widely used region is of course the mid-infrared that extends from 670 to 4000 centimeters, or if you want to talk in micrometers, 2.5 to 14.9 micrometers. The infrared region from 4000 to 14,000 centimeters, that is still shorter wavelength, 0.75 to 2.5 micrometers, is also finding considerable use for routine quantitative determination, underline quantitative determination, and this is called as the near infrared region. The far infrared region has been for the determination of structures of inorganic and metal organic species, and it comes at the extreme right hand of the electromagnetic spectrum. So here are the spectral regions: near, mid and far. Measurement type for near is the diffuse reflectance or absorption for quantitative and purposes mainly. And samples should be solid or liquid commercial materials or even gaseous mixtures. Mid IR is qualitative mostly for pure solid liquids or gases, mostly organic compounds. Quantitative for complex liquids, solids or gaseous mixtures. It can be also hyphenated with chromatographic systems for complex liquids, solids and gaseous mixtures. It is mid-IR is also used for reflectance and emissions for mainly qualitative and quantitative purposes respectively for pure solids, liquids or atmospheric samples. FTIR IR is used for absorption, basically type of spectroscopy, and it is qualitative in nature for pure inorganic and organometallic complexes or chelates. So applications of IR spectrophotometry or spectroscopy can be for organic compounds, mainly for qualitative purposes, identification of functional groups and structural elucidation, identification of substances, or you can say superimposition, matching the IRs and seeing with a standard that this is this, if the fingerprint region also matches perfectly. Studying the progress of the reaction, that is reaction monitoring, like if you start with an something with a cyano group and it cyclizes to an amino group, so the starting material or the reaction mixture and the final product IRs will accordingly show the corresponding groups. Detection of impurities, if some starting material is there and if its peaks are showing in the spectrum, that means some impurity is there, and distinguishing between two again through superimposable IR. Inorganic compounds for high modes of vibrations, lower symmetry of complexes and formation of chelates, these can also be checked through infrared spectroscopy, but far infrared spectroscopy. Miscellaneous examples are determination of purity, like quantitative for near, particularly shape of symmetry of molecule, presence of water in a sample, you get very broad bands. Measurements of paints and varnishes, again you are talking about near infrared spectroscopy. Examinations of old paintings and artifacts and their ages, again this is near. Greenhouse effect, detection of automobile, and there are many uses. For a qualitative analysis, computer search systems, virtually all infrared instrument manufacturers now offer computer search systems to assist a chemist in identifying compounds from. They have data banks of stored infrared spectral data. The position and relative magnitudes of peaks in spectrum of an analyte are determined and stored in the memory to give a peak profile which can be compared with the profiles of the stored pure compounds. The computer then matches these profiles through fingerprinting and prints a list of compounds having similar spectra to that analyte. So usually the spectrum of the analyte and that of the potential match can then be shown simultaneously on the computer to display the comparison. So it's so automated that you don't have to use your give much stress to your brains. It does automatically, and it picks up from the database which spectrum is matching with your unknown and brings it on the, it overlays them actually for a nice comparison. For quantitative applications, quantitative infrared absorption methods differ somewhat from ultraviolet visible molecular spectroscopic methods because of the greater complexity of the spectra, the narrowness of the absorption bands, and the instrumental limitations of IR instruments. Quantitative data obtained with infrared are generally significantly inferior in quality to data obtained with UV visible spectrophotometers. So as far as quantitative applications, IR finds less applications compared to UV visible, and this is because the narrowness of the absorption bands and their pure quality, and they are much complex, so it's very difficult. Okay, like therefore it's transmittance also, if you try to see, much complex. Mid-infrared reflection spectrometry. Infrared spectrometry has found reflection spectrometry, not absorption. Now we are talking about reflection spectrometry, has found a number of applications, particularly for dealing with solid samples that are difficult to handle, such as polymer films and fibers, foods, rubbers, agriculture products, and many others. Mid-infrared reflection spectra are similar in general appearance and provide the same information as do their absorption counterparts. Reflectance spectra can be used for both qualitative and quantitative analysis. Here we have given an example of carbazole and an unknown, and they can be matched. Now this is an absorption spectrum and this is a reflectance spectrum. That's all. An example of IR determinations of air contaminants, this can also be done in particularly in case of a near infrared spectrum, and you can get a very near to the actual value, and very relative error is quite less. Near infrared spectroscopy region in the spectrum extends from the upper wavelength end of the visible region, that is at 770 nanometer to 2500 nanometers, that is from 13,000 centimeter inverse to 4,000, and the absorption bands in these regions are generally overtones or combinations of fundamental stretching vibrational bands that occur in the region of 3000 to 1700 centimeters. The bonds usually are CH, NH, and OH. Because the bands are overtones or combinations, their molar absorptivities are low. And far infrared spectroscopy, the far infrared region is particularly useful for inorganic studies because absorption due to stretching and bending vibrations of bonds between metal atoms and both inorganic and organic ligands generally occur at frequency lower than 650 centimeters inverse. And for example, heavy metal iodide generally absorb in the region of 100 centimeter inverse. So far infrared studies of inorganic solids have also provided some useful information about lattice energies of crystals and transition energies of semiconducting materials. So thank you very much, and this is the end of our fourth video. We may proceed for another part, and that is we can actually go for the question banks in the next video.